Hi, it's Miss Elizabeth. Welcome back to Rock Island Public Library Summer Math Program. So this time I just want to point out that I know when you're here in person I usually read you a story, and I'm going to just point out one of my books that I enjoy reading. So Cindy Nishwander has written a number of books about circumference, and this is one of the newer ones. Circumference Gets Decima's Point. So it's about decimals, and one of the things I love about these circumference books is they're funny, their illustrations are great, and there are ways to think about math with a story, and I think that is super helpful. So don't forget to come down to your public library and check out some math books to read this summer as part of your summer math club. All right, today you need to look in your packet and you need to find 3 sheets of paper. So the 3 sheets of paper say, okay, it looks weird. So this word here is Eulerian. Eulerian. Euler was a mathematician. He was a Swiss mathematician. And actually, a lot of things were in math we can attribute to Euler. So that is how we pronounce Eulerian Circuits. So you should have this paper, you should have this paper, and you should also have the Euler Characteristics. So we're going to go through and talk about the first one, the Eulerian Circuits. So this is graph theory. What do we do with graph theory? Well, graph theory is used for how things are interconnected. So this is something that people who are working with electricity or folks who are thinking about the internet, we're just going to look at these circuits. So this is also math. Who knew? So the first thing we're going to do, it says trace these shapes, start and end on the same vertex or dot. So the vertex, like I explained to you before, is the corner. So like this right here, the pointy corner would be the vertex. So you'll notice that on a star, we have 1, 2, 3, 4, 5 vertices because it's a pentagram. Penta means 5. Over here we have a little house with a chimney. So if we didn't have the chimney, that would be a pentagon. But because they added the chimney, we have some extra sides. And that also means we have some extra vertices. Down here, we have this star of sorts, and it has 1, 2, 3, 4, 5, 6, 7. So it has an odd number of vertices. And we're going to look and see, can we trace over every edge, because the edge is the line, and we never lift our pencil. So you try this at home. Start with a star and see if you can draw it, starting at any one of the points and tracing all of the lines and coming back to where you started. I just gave you a hint with my finger right there. And see if you can do it without lifting your pencil. You try it. Did you try it? I know that this one I showed you with my finger. If you could start at any point and you go down and up and over and down, and there it worked. This one you can see very easily that you're going to be able to go around the shape. You know, when you go around a shape like that, that's called, in this case, the perimeter. Here we wouldn't call that the perimeter because we're not doing this outside line. We are actually doing all the lines. This one is also a perimeter. So perimeter is always going to work to be able to do that. And these 3 shapes are not going to have the simplicity of these 2. But each one of these should be like this one. And you should be able to start at a vertex and trace this and come back to the vertex that you started without going over one of the lines you've already gone over and without lifting your pencil. I'm going to leave that for you to do. The good thing about this is you could put a piece of paper over this and you can see, you probably can't see this on the camera, but if you have enough light through it, you can see the shape and you can practice it. You can have your parents make photocopies of it, Or you could put some kind of plastic over it and then try to do that with some kind of a dry erase marker. So I'm not going to show you how to do this. This is going to be one you're going to do on your own, but it should work for every single one on this paper. Now on this paper, this one has some different shapes, and it says circle each graph that has an Eulerian circuit. And what that means is that it worked like these, that you didn't have to lift up your pencil and you didn't have to cross a line again. And what I will do is next week when you come back, I will show you which ones worked and which ones didn't. And then we're going to think about a little bit why that might be the case. And we're going to talk about that based on filling out this worksheet, the Euler Characteristics. So if you have time right now, get out, after you've done these and thought about them for a little bit, I want you to take out this paper because this is the one we're going to do together right now. So the Euler Characteristic says for each graph, you're going to count the vertices, the edges, and the regions. Don't forget the outside region. Then calculate vertices plus regions minus the edges for each graph. So we're going to take the time to sit out and do each one together. So we'll count 1, 2, 3, 4, 5 vertices, because those are the dots. And then we're going to count the regions. Remember, the region is there's one on the inside and then there's something on the outside. So that's 2. And now we're going to count the edges. Well, I can see this shape is a 5-sided shape. 1, 2, 3, 4, 5, because it's a pentagon. So I write 5 here. And we notice the same thing happens. 5 plus 2 minus 5 is going to equal 2. So we got 2 and we got 2. Let's see what happens when we get to some other shape, maybe like this one down here, because I bet you at this point you can do these. Remember when you count the regions that it's 1, 2, and then the outside is 3. I think the edges and vertices are easier to count. Let's do this one. 1, I'm going to mark it. 2, 3, 4, 5, 6, 7, 8, 9, 10. And then my regions are going to be, this is 1, 2, 3, and then the outside is 4. And the edges are going to be a little tricky to count, I think. So I'm going to use my crayon to help me. That's technically an edge between those two. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then what happens? Well, we have 10 plus 4 minus 12. And that equals 10 plus 4 is 14 minus 12, and that is 2. Oh, it's the same. These, you'll notice, will not give us the same answer. And you'll find out, we'll kind of look to see what's going on with these two in a minute.